All right.
What is it that's so special about your video compression algorithm that makes it work so much better than so many other algorithms that just got grouped into everything else in this case?
Well, there's a ton of stuff in there. For one thing, it's not based on group of pictures. And I mean, we could do motion JPEG, just compress every frame. That's a low latency way to do video compression as well. But the frames are huge. You'll end up with HD TV running at over 100 megabits a second, which is just not practical. Even in countries where they have connections like that, it'd be too expensive to carry through the internet and so on. So we had to go and rethink the way you do video compression. And we ended up utilizing perceptual science and also a bunch of mathematics and so on. Then there's another thing mixed into this, and that is the unreliability of the internet. The fact that we've got this jitter, we've got packets lost, we've got packets out of order, we've got competition for bandwidth, where the bandwidth goes down and up because your kid brother's watching YouTube or something. So we had to go and deal with all of that stuff, and that's all wrapped into the algorithm. So there was tons of errors going on. Any connection is going to have packet loss, especially going over 250 miles. So there are tons of errors in these demos. There's right now tons of packet errors going on. And I don't think you see them. Has anyone really noticed any failures here? If you haven't, then we've done a pretty good job. When we got this thing first working several years ago, it worked. We got it low latency, but it was not reliable. I mean, it would work if you're lucky, but if you took it somewhere else and someone else's connection, there was congestion that day, you were doomed. All right. So it doesn't. I mean, it's just a matter of success of a lot of refinements. There's both a lot of engineering and then a lot of practical refinements that have gone into it. Next question.
Yeah, just a follow-up question about the compression algorithm. Is your compression algorithm lossless, or
is what?
Is your compression algorithm lossless, or has some loss of quality when from the server to the client?
Oh, does it lose anything? Okay, so the question is, does the video compression algorithm, I think, lose anything on the way here? Sure it does. And so we don't have, so conventional video compression algorithms, because they already introduce lag, can you just kind of lower the volume of the speaker here, and I'll just kind of leave this running with the spectating going. So are those iPhones still going around?
Yes, one's down there.
Oh, okay, good. And people are still playing this thing? Oh, yeah. Or someone's using this or not? You are. It doesn't work? Oh, you got to push the button, the power button. It will power down after a while, or it may be too far away. Oh, you got it working? Oh, you're in the intro. This game takes a long time to get. Have you played Mirror's Edge before? Oh, okay, good. I'll leave you to it. All right. So, anyways, the compression algorithm, it does lose stuff. And a conventional compression algorithm, because it's very high latency, usually it's sent over HTTP. And if there's a lost packet, it goes and says, hey, give me that packet again, right? We don't have that privilege. We barely can make this thing work with one round trip. So we're using UDP, and we go and send the controller input up. It sends the stream down, and if something gets lost, we have to deal with it. We just have to deal with it. Now, there's a certain amount of stuff you can deal with mathematically, all right, but we have very tight bandwidth constraints. We can't just send everything twice, and so on. So we have to go and be very smart about it. And what we've done is a whole bunch of stuff, which is, on the range. Some of it's error correction, some of it's error concealment, some of it is psychophysical stuff where we're dealing with these imperfections, and it all had to roll back up to the bigger picture of the algorithm. So the thing that's different about this compression algorithm is that it is based on a feedback loop. Existing compression algorithms, basically are set up to be one-way streams. This one can't operate that way. I mean, literally, we're getting feedback within a frame time, within milliseconds. So we have to go and we've made it to be adaptive. Now, remember I showed you here where you can spectate like on a baseball game, and like have 100,000 people spectating while you're playing baseball. Now, wait a minute. If I've got a compression algorithm that relies on a feedback loop, how can I have 100,000 people with feedback loops all going and changing the compressor? What's it going to compress? So here's how we solve that problem. We made it so we do two simultaneous compressions. One compression we do is based on this an algorithm, which is this high feedback perceptual algorithm that is constantly adapting for the individual user who is playing the game. All right. The second compressor is doing a compression that's a one-way compression. That's a high-quality compression where everything's perfect all the time, and it's then distributed. And we have plenty of bandwidth in the data center, so that's distributed at high bandwidth using IP multicast through for a cascading set of switches to all the different servers who are spectating on it. So by doing 2 simultaneous compressions, we solve it. And that serves another purpose on the Bragg clips, for example. The Bragg clips are not recorded from what we call the live compressor. The reason is the live compressor looks good when things are in motion. Okay, take existing compression algorithms. If you stop them on a frame, that's how DVR works, like TiVos. If you stop them on a single frame, every frame looks good with conventional compression algorithms, okay? And that's why pause works for DVR. But when you go and stop our algorithm on a single frame, it might look good, it might not. We made the algorithm only have to look good when things are moving. Because if someone does do a Bragg clip and then hit pause, they didn't record the live stream, we recorded the media, what we call the media stream, which every frame is perfect, okay? Whereas in the live stream, every frame is perceptually good when it's in motion. So we relieved the constraints on the compression algorithm, and that's how we solved the problem. And so that's a lot of things that you guys got to do. It's like, I can't tell you how many times I sit with engineers and they go and say, well, this is a law. Like someone was telling me about Shannon's law. I mean, give me a break, dude. It's not a law, okay? It's a limit, all right? And we have a technology we developed which goes, we're seeing over 100x Shannon in a wireless channel, okay? And so the thing is, and so he said, that can't be. How can you get 100x Shannon? It's not that not that we're breaking Shannon's limit. It's not that Shannon was wrong. Okay, Shannon was asking the wrong question. He had the right answer, but for the wrong question. Okay, that's how we were able to pull this thing off. Okay, for compression, okay, it's not these other compression algorithms weren't optimized to the best they could be. They had constrained themselves to every frame's got to look good. Okay, and we said, all right, we don't have that constraint. We're going to do 2 compressions. One compression where every frame looks, the thing looks good in motion, which is great. I mean, who cares? If it's moving, it's moving. And then we have a second compressor where we make it so that every frame looks good. And that also solved the problem because we can IP multicast a unidirectional stream. Long answer, short question. Yes?
My question is something like this. With current, for example, laptops like a MacBook, you can compress 30 frames per second utilizing the whole CPU. Which
Yes.
means for each frame you will spend 33 milliseconds.
Yes.
30 milliseconds. So in this case, how you are get rid of this 30 millisecond encoding time? Just encoding immediately.
It's not encoding. This is decoding.
No, I mean in this.
Oh, it's done in hardware. I'm bummed because I should have brought one of our compressor boards, which has.
So you have a customized hardware which
Yes.
compress like
Yeah,
in less
it's
than
a little
like
chip.
in a
draws-
few milliseconds it's compressed.
Yeah, so we developed the algorithm on dual quad-core Xeons, with like $5,000 8-core machines. Okay, and the algorithm could just about run. It could run in real time. Actually, it ran just about a little south of 60 frames a second, but it could run almost in real time. And we were able to debug it and get the basic thing work. Then it was reduced to silicon, and so this thing, which is drawing like 350 watts, and it's 5,000 worth of thing. First 5,000 is worth of server to do a compression. We reduced to a $10 chip that draws 2 watts. Okay, nice. So we could drop 2 of them on a board. When we were developing this thing, we literally had a dual quad-core Xeon for the live stream and a dual quad-core Xeon for the media stream. So it was $10,000 for each user. That's what we started with this thing. All right, and now we're down to, of course, where each user, it's I don't know, $25, $30, something like that. So it's a huge, huge difference. But of course, it all comes down to this. I mean, those dual quad-core Xeons are completely general-purpose machines. You can use them for anything. These chips here are useless for anything other than what they're made to do, which is very, very efficient compression of this algorithm.
I see. So each of these chips, how many of them are controlled by a single system?
Well, there are 2 chips for every stream, but
Okay.
each system may have more than one stream. Like we're virtualizing, then we'll have then it's 2 chips for each. 2 chips for every stream, because we have a live stream for each user, and then we have a media stream also that goes out as IP multicasted.
All right.
Thank you.
On the business end of things, when you're in the business end of things, when you're providing these games over the internet, are you selling them for the same price that they would be available in the store at $60 per se for Crysis?
So we are not. So the way a business works is we'll go and go and like just give you something else to look at. We are the way it will work. If Xbox Live, there's a base fee you pay. So okay, so we'll have a base monthly fee if you want to sign up for Onlive. If you just want to demo games, that'll be free. So you just go wild. because we get paid by the publisher for the games, and they're happy if you use them and buy them. Okay, but if you want to use the service, then you pay a fixed monthly fee, and then the games are sold a la carte. I mean, you can rent them, you can buy them, you can get a subscription for them, you can, you know, they'll bundle them into different packages. Now they're talking about making games that are episodic, so you like go from stage to stage and buy them in pieces. Then there's going to be other business models, like, you know, you'll have some advertiser supported thing, or ones that you buy stuff, you know, in the world that you're in, you know, so you have, you know, I don't know, you buy some new armor or something, or whatever it is you're going to do, or you know, some furniture for the house, you know, whatever it is. So there's many different business models that can be supported by this. So that's why we just have the base fee, which lets you get on, go wild. Then after that, we let the publishers do whatever we want, and we do a revenue share with them.
All right. My second question is, it seems to be that the system, or is it okay to refer to it as a system?
Yes.
All right. That the system is it's one player per screen. Is this true?
No. Well, it depends on the game. If it's a one-player game, yes. But like Lego Batman is a two-player game. And let's see. I think we have Lego Batman. Yeah, here it is. Yeah. So here's a two-player game. I mean, I don't even know what constitutes the best player of Lego Batman. But anyways, apparently some criteria that is used. But in that case, if you have two controllers, then one person's Batman, the other one's Robin, until you switch over the Joker. But here's what's really cool about that game. If you've got a kid and you're on a business trip, your kid can play Batman on a micro console, and then you can play Robin at a hotel, and you can play together and talk with voice chat, which is kind of cool. All right, yeah, let's get into this thing here. Does anyone know how to play Lego Batman? I think it's like the usual keypad thing.
Yes.
All right. Oh, one more? Okay. Let's just do that. Get that
My
going.
last question.
Okay, good. Yeah.
My last question is the competitiveness with an interactive system. Like,
Yes.
A lot of systems these days are seeming to focus on how we can turn into a 6-axis controller or a Wii type of play.
Yes.
Does your system, will it support anything in the future for motion?
Absolutely. So there's no, what we do is so we've got, you know, USB ports on here. I don't know where the nice box is, but you can hook up any controller to it. You could hook up a guitar to it. You could hook up a 6-axis motion controller if that's what you want to do. All those things are fine. God, there's so many screens to skip on this thing. I think I'm finally in the game. Yeah, there I am. I'm controlling Batman. Okay, there he is. Okay. All right, good. Yeah, all right. So does this work with the controller? I think it does. Someone have the controller here? Oh, no. Yeah, there you are. Okay, so I don't think we have another wired controller, but